Let's solve problem 11. A vector field is given by f of r equals this huge vector, which I already wrote in column form here. So you can see this is x, the x component of the vector field, which is a function of x, y, z, the y component of the vector field, function of x, y, z, and the z component of the vector field, a function of x, y, z. Verify whether it derives from a potential and find the potential if it exists. Okay, so let's do it. First of all, how do we verify if it comes from a potential? So to verify if f is equal to the minus gradient of some scalar potential, we know that this will happen together with the fact that the rotational of f, or the curl of f, will be 0. So f will be irrotational, right? At least this was true if the field is defined in a simply connected region, which is true right now because these are just normal polynomials which are defined everywhere in the three-dimensional space. So we know that if we check the curl of the field f and we find that it is equal to 0, we will be able to say that this field derives from a potential. So let's calculate the curl of f. Curl of f is the nabla cross product f, which means this. X hat times the determinant created when you cross out that row and that column. Plus y hat times the determinant created when you cross out this row and this column, but with a minus sign. So it will be this times this minus this times this. Plus z hat times the determinant created when you cross out that row and that column. So let's start calculating our partial derivatives. Partial of fz with respect to y. Minus partial of fy with respect to z. Plus y hat times partial of fx with respect to z. Minus partial of fz with respect to x. Plus z hat times partial of fy with respect to x. Minus partial of fx with respect to y. So now you notice that every single term cancels out with the corresponding term here. This cancels out with this, and this cancels out with this. So therefore the answer is 0 x hat plus 0 y hat plus 0 z hat. So the curl of this vector field is 0. Okay? And therefore this field derives from a potential. So now the thing is, we need to calculate the potential from which this field derives. There are many ways of doing this, but one of the ways, which is the one I have taught you, which I think is the simplest, is to do it by doing an integral. So you know that the integral from the origin to any point r of f dot dr gives the potential at the origin minus the potential at any point r. Okay, and therefore if we solve for the potential at any point r, we find that this is equal to the potential at the origin, which is just a reference constant. Okay, we can call it phi 0, minus the integral from 0 to r of f dot dr. So now we can do this integral in any way we want, okay? So actually, I could, if I wanted, do this integration by creating a straight line between 0 and r. So if r is some point here, yeah, it has some z, some y, and some x coordinates. So this is r. So one way I could do it is I could write the parameterization of a straight line going from the origin to r. And I could do that integral, and that would work, and it would be a perfect result. But I'm going to do another approach, which is taking a long path, but which makes the integral simpler. We integrate first along x until we arrive at this value of x. Then we integrate along y, along this path, and we arrive at this value of x and y. And then we integrate along z, following this path. Okay? So we are going to take that option. So for that, I will show you two ways. One, following the recipe of parameterize the curve, find dr, do the dot product to evaluate the integrand, and calculate the integral. The 4 steps for each of the 3 segments of the path. That will be the long method. After that, I will show you how it can be really fast to do it, everything like in 3 or 4 lines. Okay, but first let's do the long method. So we start with our first integration. Let's call these paths, let's call them C1, C2, and C3. Okay, so the integral from 0 to r of f dot dr, we can call it our integral I, and it will be equal to I1 plus I2 plus I3, corresponding to each of the 3 paths. Okay, so we are going to do each path at a time. So I1. Let's parameterize this curve. So this is very easy because we have to do a curve that goes from the origin to a point x0, 0. So the first step is to parameterize the curve, and since we are moving along the x-axis, I'm going to use a parameter which represents the x variable. Okay, so I'm going to say that our curve r of u is simply equal to u, 0, 0, where u is going to change between 0 and our value x. To make sure that we don't get confused, because here x, from the point of view of the integral, x, y, and z are going to be a constant, right? So I'm going to call them x0, y0, and z0, okay? So that this is now x0, this is now the point x0, y0, and r is the point x0, y0, z0. And that way we will not be confused when I say that the limit is from 0 to x, because I can write from 0 to x0. And we know that that is a constant limit of integration. Okay? So step 2 is to find dr. And dr is simply dr with respect to u times du, which is equal to 1, 0, 0 du. Step 3 is to evaluate the integrand. So we have to do f dot dr. So we have to do our vector field dot dr. And you can see that this will result in fx times du. Okay, so that's very simple, and that's one of the reasons why we are going to choose these paths, because here dr will be 1, 0, 0 du, here dr will be 0, 1, 0 du, and so on. You will see that it will make the dot products very easy. But we still have to substitute f of x at the curve. So f of x is this equation here, I squared minus 2xyz squared. And it turns out that this, z cubed times du, but we still need to substitute x, y, and z by their values, right? So we need to substitute the fact that x equals u, y equals 0, and z equals 0, because in this path you see that y is 0 and z is 0. And therefore our result is 0 minus 0, 0 du, such that the integral is going to be 0. Okay? Next, let's do I2. So in this second integral, we are moving from x0, 0, 0 to x0, y0, 0, which means that during this integration, x is going to be constant, it's going to be equal to x0, y is going to be our parameter, let's call it u, and z is going to be constant because it's going to be 0. Okay? So we can parameterize this curve. Step 1, parameterize r of u. I said we keep x constant to x0. We keep y as our parameter, which let's call u, and we keep z constant equal to 0, with u changing between 0 and y0. And this parameterizes this straight line. Now, step 2 is to find dr. And dr is just dr over du times du. So we will get 0, 1, 0 du. The next step is to evaluate the integrand f dot dr. And this will be equal to, we are going to do the dot product with 0, 1, 0, so we can only keep the y component. So this will be fy times du. Now fy is this component here, 3 plus 2xy minus x squared z cubed. So we can write it here, 3 plus 2xy minus x squared z cubed times du. And now we have to substitute the values for x equals x0, y equals u, and z equals 0. Because we need to evaluate the integrand at the curve. So when we do that, we get 3 plus 2x0u minus 0 du. Perfect. So then the fourth step is to do this integration. So it's the integral in u between 0 and y0 of this integrand. And the result is simply 3u plus x0u squared between 0 and y0, which is 3y0 plus x0 y0 squared. Okay, very good. Now we have to do the third path. So the third path is this path here. So in this path here, let's think about it. So x is equal to x0, we don't change x. Y is equal to y0, also a constant. And z is our parameter, z equals u. Okay, and by changing u between 0 and z0, we will go through that straight line. Okay, so that's what we are going to do for I3. So we parameterize the curve, which means that our curve as a function of u is equal to x0, y0, u, and u is changing between 0 and z0. Next, we need to find dr. dr is the dr over du times du. So we find the derivative of this with respect to u, and we get 0, 0, 1 times du. So it's only along the z hat direction, as expected, because this straight line is going straight up. So step 3 is to evaluate the integrand at the surface. So f dot dr. Since dr only has a z component, we can say that this is equal to fz times du. Right? I'm doing the dot product between fx, fy, fz and dr, which is this vector here. So now we substitute f of z. So I can copy it from my other screen. It's equal to 6 z cubed minus 3x squared y z squared. But now we need to substitute x and y and z from the curve. So x is constant and equal to x0, y is constant and equal to y0, and z is equal to u. So what we get is 6u cubed minus 3x0 squared y0 u squared du. So that now in step 4, we are ready to do the integral. I3 equals the integral from 0 to z0 of 6u cubed minus 3x0 squared y0 u squared times du. So doing this integral is very simple. It's just u to the 4, but we will need 6/4, which is 3/2 of u to the 4, minus u cubed, but we will divide by 3, so 1, so x0 squared y0 u cubed, evaluated between 0 and z0, which will simply be equal to 3/2 of z0 to the power 4 minus x0 squared y0 z0 to the power cubed. Okay, and with that we have found the three integrals I3, I2, and I1 that constitute the entire path integral. Okay, so let's write down this. Let me copy this here, or let me first copy the fact that the integral is equal to the sum of the three integrals, so that we can now write the sum of the three integrals. The first one was 0, the second one was 3y0 plus x0 y0 squared, and the third one was this one, 3/2 z0 fourths minus x0 squared y0 z0 cubed. And this is the integral between 0 and the point x0 y0 z0. Now we can write that the potential at any point, let me copy the equation from up here, this equation here. So the potential at any point is equal to the potential at the origin minus the integral between 0 and any point r of f dot dr. So if we call this point r, we call it x, y, z, so any point r, we can just use this expression but changing x0 to x, y0 to y, and z0 to z. Okay? The only reason I did this intermediate notation of using x0, y0, and z0 for doing the three integrals is that I wanted to make sure that it was clear to you that, for example, during this integration, x is equal to x0 is a constant. It's not a variable, okay? So that when you are doing this integral number 2, and you see that the integrand is 3 plus 2x0u, you don't say, wait a second, we have an x here. We shouldn't have x's. We should only have the parameter u plus constants. So that's why I used the 0 subscript, so that it's clear that x0 is a constant. It's not a variable, okay? So that is why I used x0, y0, z0 for doing the three integrals. But after we know the analytical solution between 0 and x0, y0, z0, we can now just drop the subscripts, because that will be the integral from 0 to any point x, y, z. So therefore, this will be equal to phi 0, and now minus all of this, but without the subscripts. Okay, and that's our potential at any point r. It was quite long, I must admit. Now, can we check if this potential is actually the correct potential? Now it's very easy to check, because even though going from f to the potential is very tricky, as you just saw, going from the potential to f just involves doing the minus gradient. So it's worth checking that. So now we can check, is f equal to the minus gradient of phi? So to check that, we just need to do the minus partial derivative of phi with respect to x, the minus partial derivative of phi with respect to y, and the minus partial derivative of phi with respect to z. So now we have to do three partial derivatives. The partial derivative of phi 0 will always be 0. That's why the constant is an arbitrary constant. We don't care about that constant in the potential, because when you do the gradient, that constant will go away. But so the derivative with respect to x with a minus sign will be 0. Let me put the minus sign outside, otherwise it's going to be a bit confusing. So I can do the partial derivative with respect to x. So it will be 0 minus y squared plus 0 plus 2x y z cubed. Then the partial with respect to y is going to be minus 3 minus 2xy minus 0 plus x squared z cubed. And then the partial with respect to z, that's going to be 0 minus 0 minus 0 minus 3/2 times 4, that's going to be minus 6 z cubed, plus 3x squared y z squared. And now we apply the minus sign, so we get y squared minus 2xy z cubed, 3 plus 2xy minus x squared z cubed, 6z cubed minus 3x squared y z squared. So, is this the original vector field that we started with? So we have to compare this with this. And the answer is yes, it is. So it worked. Okay, let me double check that with my other screen. Yes, that's correct. So we have very quickly checked that the scalar potential that we found is indeed the scalar potential from which this vector field derived. Okay, so we have found the scalar potential for a vector field. This was the long path, but let's do it in a shorter way. So we begin the problem by saying that our potential at any point r is equal to phi 0 minus the integral from 0 to x0, y0, z0. And this will be, by the way, let's call it this the potential at r0 of f dot dr. Okay, so now we can write that this is equal to phi 0 minus the integral in x from 0 to x0 of f dot dr. So this is the first integral, yeah, the first path. Then the integral from 0 to y0, but x being constant. So maybe I should write here the actual 0, 0, 0 to x0, 0, 0. Then from x0, 0, 0 to x0, y0, 0. And finally, the last leg of the path is from x0, y0, 0 to x0, y0, z0. F dot dr. Okay, so I have written the integral in 3 legs, as you know. But now we know that dr in this case will simply be dx because x is the only parameter that is changing while the others are constant. Okay, so therefore we could write this as phi 0 minus the integral from 0 to x0 of f x component times dx. Okay, so I already assumed, because from experience after having done many problems, I know that dr will be just dx in x hat direction because only x is changing, and therefore the dot product of f dot dr will simply be fx times dx. Okay, the next integral will be the integral from 0 to y0 of fy dy, but keeping, so here we are going to keep y equals 0 and z equals 0. Here we are going to keep x equals x0 and z equals 0. And in the next integral, which is along z, from 0 to z0 of fz dz, but we are going to keep x and y as constants, because those are the constant values that they have throughout the whole integration. Only z is changing. Okay? So very good. So now we are ready to do this integral. So we just substitute. So I have, let me first copy the entire function. So fx is y squared minus 2xy z cubed dx minus the integral 0 to y0 of fy, which I can copy entirely, and it's equal to 3 plus 2xy minus x squared z cubed dy, and now minus the integral from 0 to z0 of fz, which I can copy entirely, it's equal to 6z cubed minus 3x squared y z squared dz. But now we need to substitute these things that I wrote here. So we need to make y equals 0 and z equals 0 in this first integral. because those are the constant values of y and z. We need to make x equals x0 and z equals 0 in this second integral, and we need to make x equals x0 and y equals y0 in this third integral. So that our result is phi 0 minus the integral from 0 to x of 0 dx minus the integral from 0 to y0 of 3 plus 2x0y minus 0 dy minus the integral from 0 to z0 of 6z cubed minus 3x0 squared y0 z squared dz. And now I can do these integrals very simply. So this integral was going to be 0. This integral is simply going to be 3y0 plus 2x0 y0 squared, without the 2, sorry. Yeah. And this integral is going to be 3/2 of z0 to the 4th. Yeah, so that when we multiply by 4, we end up with 6, minus 3 over 3, which is 1, x0 squared y0 z cubed. Okay, so we instantaneously do the integrals. By the way, this is the whole integral. So you have seen that we can do those integrals in our head. So we get phi 0 minus 3y0 minus x0 y0 squared minus 3/2 of z0 to the 4 plus x0 squared y0 z0 cubed, and that will be phi at any point r0. So now we could just say that we can rename x0, y0 and z0 by x, y, z, so that we get which is our final answer. Now there's actually a second section for this problem, which is problem 12, which says, use the previous result, which I have copied here. This is the scalar potential, to find the line integral of f.dr between these 2 points, 0, 0, 0 and 1, 2, 1, along any path from the point 0, 0, 0 to 1, 2, 1. So I have drawn here an example. We have the xyz space, and we are asked to calculate the line integral along any path. Okay, so therefore the line integral between these 2 points of f.dr, we could calculate it like we just did, right? We could do a line integral and we could choose any path we want, and the result would always be the same. And the point is to show that you don't have to calculate a line integral anymore, because now we know what the potential is. So since this is a field which derives from a potential, we can write this as the potential at the origin minus the potential at 1, 2, 1. Okay, so we just have to substitute x equals 1, y equals 2, z equals 1 into the expression here, and we get that this integral is equal to the potential at the origin minus, and now I'm basically going to copy this, but substituting those values. And you can see that the constants will cancel out, which makes sense because the constant phi 0 was not included in the vector field f, and therefore it wouldn't make sense if the line integral depended on the constant. So of course you are subtracting the potential at the origin minus the potential at another point. So if they have a common constant that is free, you are subtracting it out. So the constant always disappears, and the final answer, if you work through this, is 15/2. And that gives you the differential potential between those 2 points, which is equal to the work done by this force or the line integral in general. Okay, thank you very much for watching, and I hope you enjoyed this relatively long problem of finding the potential from a vector field. Thank you.